So now we saw the development that is bridging the parametric models with Gaussian distributions and shared covariance metrics. And we see that it is related to linear discriminants. We will develop a method that is called logistic regression that is implementing somehow this idea to be able to estimate the parameters, assuming some kind of modeling, some kind of Gaussian distributed view of the data. So assuming that T are distributed according to normal distributions, we get a probabilistic interpretation of our modeling. So logistic regression means that we want to estimate the posterior. So basically, we have this posterior, and we define how it is related to linear model that way. We see that it is, in fact, the application of the sigmoid function over the linear model here. And this gets us the posterior probability for a given data X. And we can then estimate the configuration to use for that probabilistic model with gradient descent. So we are no more trying to estimate the vector means, the covariance matrix. We are looking to estimate directly the W and W0 to use to get a good classification, also good posterior probabilities estimations from our sample set. So we are looking to learn W and W0 from our training set. And here we are falling back to the previous way to label our data using RT equal to 0 or 1. So it's no more -1 and 1. We're getting back to the 0, 1 representation of labels for our training set, data set. So if we say that, for instance, our RT for a given XT is following, so all RTs for all XTs are following some kind of Bernoulli distribution, and this is configured, parameterized according to the YT, which is basically the posterior probability. So we know that somehow the RT should be following, so the label should be following a Bernoulli distribution, which is a 0-1 distribution, based on the posterior. And that makes sense, if we say that, okay, this X is from class 1 at 75% probability, so at 0.75, then we assume that in real life, we've got 3/3 of the time we have that label and 1/3, 3/4, so 75% of the time we've got one class, and 25% of the time we've got the other class. So basically, we see that RT is following a Bernoulli distribution parameterized by the YT here, given, and this is for the specific XT that we have at N. For a different XT, the values are different, of course, because the posterior is different for different XT. From that, we will get back to the likelihood thing. So we will define a likelihood of sampling the training set big X based on our parameters Y and Y0. So this is the same maximum likelihood approach that we used before, and we are applying this here. But given that we assume the RT are Bernoulli, we will get this. We are simply getting that the likelihood is equal to the product over all samples of YT RT times 1 minus RT power 1 minus RT, 1 minus YT power 1 minus RT. So we define as error the maximum. So we want the error is to maximize the log likelihood. So in fact, to minimize the log likelihood. So we have as error here minus log of the likelihood we have here. So basically applying the log on the product, we have a summation, and then we just replace all these things with using the effect of the log. So we have something like that. So we have the summation of RT log YT for the first step plus 1 minus RT times log 1 minus YT. This is simply applying this and getting as error the log likelihood. So this error is also named the cross entropy. So we call this the cross entropy directly. And this is kind of common in machine learning as criterion. And as such, if we go into our function, we want to get the derivative of the sigmoid function first, because we want to obtain a gradient. So remembering that y is equal to 1 over 1 plus exponential minus a, which is directly the sigmoid function, developing this and getting the derivative of y according to a. So this is kind of abstract, but that's required to maybe split the developments into steps. We have that thing. So the derivative of our function here correspond to that if we just apply the functions. That is not super complicated, but relatively not convenient. We can get something better in terms of managing the equation. So let's develop this saying, okay, let's decompose this. We have like divided by 1 plus exponential minus a power 2. So let's just split this in 2. Let's split this in 1 plus exponential minus a times 1 plus exponential minus a. So basically expanding the power of 2 into 2 components. And on the top at the numerator, we just kind of use a small tricks of saying plus 1 minus 1, which is perfectly fine because it is equivalent to 0. But doing this is interesting because we can get this thing, which is basically 1 plus exponential minus a divided by 1 plus exponential minus a. So this is equal to 1. Further simplifying this, we've got something like that. So this is still here. That's fine. But that thing, given the simplification, so that thing here, given the simplification we have done, it is 1, which is what we have before, minus 1 over 1 plus exponential minus a. Yes, okay, yeah, fine, but yeah, it's not simpler. Look, we have that thing here, we have that thing here, and these are corresponding directly to the y. So we can get this simplified as y here times 1 minus y. So that formulation is kind of super simple. We've got the derivative of y equivalent to y times 1 minus y. So then, if we are looking at the gradient descent, we can do on that cross-entropy error criterion, we've got something like minus eta, partial derivative of the error over wj, is equivalent to minus eta. So we have the partial derivative of error over y and partial derivative of y over wj. This is basically applying the chain rule in derivations to kind of decompose our initial partial derivative into 2 components. And so this component here can be stated as something really similar to that. Not exactly, but really similar. So we've got this thing here. So this is, we leave you the development of these equations. And we have, but the point is that with these equations, which seems to be relatively complicated, we can make a lot of simplification just by getting through this and using algebra to minimize, simplify the equations. We've got that equation here. So basically it's equivalent to eta summation over all samples RT minus YT times XJT. And for W0, the delta W0, the modification to W0 correspond to that thing here. We have error over W0, which is using the chain rule, something like this, and making the developments, we get something like that. This gives us a new algorithm for discrimination with logistic regression. So basically, we have the same pattern with a small difference. First, we are looking at randomly initializing the weights. But it appears that initializing the weights at 0 is not a good thing. It's not working well with logistic regression. So we need to initialize it to small, really small values. We are using values evenly, like uniformly distributed in that space. So minus 0.01 to plus 0.01. And we repeat until convergence the estimation of first the YT, which is basically the sigmoid over the linear model for all samples. And from that, we are updating the YJ, the WJ, sorry, that way, and updating the W0 that way here, and repeat this on the samples along the way. If we are looking at some kind of problem, you know, we can model by this. You know, we have here a simple problem taken from Wikipedia, where on the x-axis, we are looking at the hours studying an exam, and on the y, the probability of passing that exam. And of course, when you don't study much, you get a lower probability of passing your exam. So these guys has failed, and these guys has passed. So it seems that more studying means better chances of passing the exam. And then modeling this with our logistic regression get us with that function. So basically, that's the probability at, according to the number of hours studied, of passing the course. You know, at over 4 hours, it seems that we are over, I would say, 80% of chances of passing the course, according to the small samples that we have. So we've got the logistic regression developed. So this is a kind of a big, I would say, loop over getting this applied to parametric models. But you know, there is, in fact, many possibilities. So we've got 3 of them so far. We've got the perceptron rule, which is okay for linearly separable samples, not working well with non-linearly separable samples. But the equation basically boils down to an error criterion, the perceptron criterion, which is that thing, basically summing over all misclassified samples, the product of the label R and the h of x for the x misclassified. We have the least square error, which is that thing here, which is basically a regression criterion, but we can apply this for classification with better results, but not necessarily the best ones. And we have now the cross entropy, which is the criterion for logistic regression, where we are not working directly on the linear model. We are applying a sigmoid function over that linear model that allow us to obtain a probabilistic modeling, because the y here correspond directly to the posterior of C1. And that implies to change the optimization criterion and using the cross entropy, given some assumptions that are verified according to what we have done, that give us this error. So we have 3 different errors for 3 different solutions. But there are some other performance criterion we can use. All this can still be based on gradient descent after that to be optimized. So for example, we have what we call linear discriminant analysis. So these are kind of models, parametric models, but not based on optimizing directly with maximum likelihood the parameters of functions. This is based on specific criterion, like here to separate the class averages. So we have 2 classes. We are assuming that they are normally distributed. So we're using Gaussian distributions, but we have a criterion to optimize this thing such that we want to maximize the distance between the means of the 2 classes, but we are dividing this by the variance. We want to reduce somehow the variance of each class. So this is, I would say, relatively fancy, but that allow us to make interesting stuff with some kind of linear model, and this criterion is useful for that. We also have what we call the hinge error function. So the hinge is basically to make such models. So it's like the perceptron, we are making the sum over the misclassified samples, but not exactly the misclassified. We are looking at the samples where the product of RT and H of XT is smaller than 1. It means that we can get some samples that are well classified, but their age value is less than 1. And with age function, it means that they are really close to the decision frontier. And we want to avoid that. We want to get as little as possible samples close to the decision frontier. But yeah, we are using this to get the set of either misclassified or sample close to the decision frontier. And we want to minimize 1 minus RT times HXT. So contrary to the perceptron, we don't just stop when the data is correctly classified. We continue to optimize. We have some kind of error when the sample is well classified but close to the frontier. So we tend to place the hyperplane away from the samples as much as possible. And so we see, in fact, that the data from X in Y are in the margin. So this is kind of the security margin close to the decision frontier. And this is used in SVMs, which will be presented next week. So this kind of sneak preview of what we will get into next week. We also have what we call the log loss function. So the log loss function is basically that equation. So that's another one that can be used and can be, we can optimize model with that with gradient descent. If we are looking at the function of the error, it looks like that. So yeah, you need to see that, in fact, the x-axis is the function e of x. So this is the error, the difference between r minus h x. So here we see that when we've got this kind of when we have, just looking at this thing. So maybe it's not exactly this. I think it's maybe the opposite, according to what we have as axis here, because I think that, yeah, with these values, these are big errors. So it's more something like h of x minus r, I would say. Or not even that. Anyway, then I cannot relate this directly to the e function. What we can see here is the nature of the error. You know, when we have something that look like these things, we have this step function. This is the basic error, saying that we are correctly or not classifying the data. So yeah, I know what it is. It is RT times x hxt. Oops, sorry, not well visible. Yeah, this thing. So we have like the product of RT with h of xt. So with the what we call the 0,1 function, this is basically the 0,1 loss. We have this really step function that is like, okay, on the positive side, it is well classified. On the negative side, it is misclassified. This is one thing. So this corresponds to what we use for evaluating the classification error. This corresponds also to some elements that was used. I would say perceptron was not exactly this, but you know, it tends to be relatively crisp, saying that everything that is correctly classified has an error of 0, for example. Another one is the square. So the square here is what we use with the least square approach when we are doing some kind of regression for classification. So with the square, we see that, okay, on the left side, it makes, sorry, on the left side, it makes a lot of sense here. You know, we have this kind of shape. So it means that as we are far away from 0, so as we have big errors, so errors going like to minus 0.1, 0.5, minus 2, the corresponding effect on the error criterion is big. And we want somehow to be close to 0. So that is right. What is not working that well with the least square is all the right side, you know, where we have this kind of error that is increasing as we go with bigger values. While here, you know, it just means that we have a data that is well classified and far away from the decision frontier. So that's why the least square is not that interesting somehow because of that. If we are looking at the hinge loss that we just saw before, the hinge loss is interesting. It's super interesting because we see that the error is decreasing as we are getting close to the 0 value. The 0 is where we start to make correct classification. So bigger error as we are far away. So that because we are really badly classifying samples far away from the decision frontier. But even if it is well classified, we have that zone here between 0 and 1, where we will get some kind of error values measured. So the data is well classified, but it is within that margin. So we could say that this is some kind of security margin where things are well classified, but too close to the frontier. And I would say the margin extend on the right side, well, on the left side, where everything really on the left is really badly classified. So the impact on the error is higher. And if we look at the log function that we just saw before, it has that shape. So it means that, yeah, it's kind of similar with the inch, except that it is smoother, you know, after 1.0, the error is low, but still there. So we tend to maybe push even further away the samples from the frontiers, but in a relative smooth way, in the sense that it doesn't put emphasis on these samples. It has more emphasis on those who are not well classified, in a position with the square error criterion, which is kind of dealing in both sides equally, while it is not the right thing to do.